Now, the nearest neighbor is an example of what we call a non-parametric technique. The linear model is a classic prototypical example of what we call a parametric technique. So let's sort of discuss those two differences. Okay, so the nearest neighbor rule, when you get the data, you're ready to go. You don't have to estimate any parameters. You don't have to learn any parameters, even though that's not the definition of learning. It's better for me to say you don't have to fit any parameters. Okay? Now, in the linear model, you have to find your d plus 1 parameters corresponding to your d features and the augmented 1. Okay, and now in the nearest neighbor rule, so you have no parameters, but and you're ready to classify. You have your final hypothesis immediately the moment you get the data, but you have to keep all the data. Okay? In order to classify in the future, you have to keep all the data. Because the test point requires you to go and search through all the data points and find the closest neighbor and then classify accordingly. Okay, and this is not too different from the k-nearest neighbor. So all the essence of the k-nearest neighbor algorithm can be understood from just the nearest neighbor algorithm. Okay, but now look at the linear model. In the linear model, you've learned these parameters. Okay, these d plus 1 weights. Now you can throw away the data. You need to only keep the d plus 1 weights. So in some sense, the linear model performs a compression of the data into these, sufficient d plus 1 weights, and those are sufficient for you to classify. Okay. Now the linear model, along with that, compression, along with this throwing away of the data and learning these d plus 1 parameters, that, makes the linear model rigid in some sense. Okay, rigid. Why? Because no matter what the data, you are going to output a line. The hyperplane that separates a blue region from a red region. And it doesn't matter what the data is. Now look at this very complicated, data that I'm showing here. Clearly that, that this data is very complicated and not linear. But the linear model always outputs a line. Okay? So in that sense, it's specialized. You've gotten good features, and you know what model you want, okay? And so and with respect to the good features that you have constructed, the linear model will work. So it's a specialized model. Okay? You have to think a lot, but it gives you this tight link from E in to E out. Okay? Now let's compare that with the non-parametric nearest neighbor rule. Well, unlike being rigid and always linear with the linear model, the nearest neighbor rule kind of bends and flexes to wherever the data is. So you see, as I've gotten all this data here that's looking very complicated, the nearest neighbor rule separation boundary sort of wiggles and jiggles around the data and gets something that looks interesting, and maybe looks plausibly correct because we have a lot of data. In other words, it's flexible. It can model the data. There are no limitations to the nearest neighbor model. It can model anything. And that's part of why it can, get the optimal performance when you have enough data. So it's expressive, it's flexible, it's not limited to outputting linear. In fact, in this case, it's outputting something very, very complex. Okay, so it's expressive and flexible, and it's generic in the sense that it's not specialized. It can model anything. So you can throw the nearest neighbor model at a machine learning problem without having to think too much about the features, providing that with respect to whatever features you have constructed, the optimal classifier is having a small out-of-sample error. Then as long as you have lots of data, okay, then the nearest neighbor will get there. Now, what does lot of data mean? That depends on the nature of this pi of x, and that lot can increase significantly as you go up in dimension. So it's still necessarily the case that you need to think about the features and keep the dimension as low as possible. Think about the features so that the optimal classifier with respect to those features can do well. As long as that's the case, nearest neighbor can get there with enough data. Enough can depend on the dimension, and enough depends on the complexity of this pi of x, the probability of plus 1 given x. Okay, so that's just to show you that there are these techniques called non-parametric. Nearest neighbor is a prototypical non-parametric technique, and the linear model is a prototypical parametric technique. And what differentiates parametric from non-parametric? Okay, so parametric is it learns parameters. It's typically rigid, outputting a hypothesis from some fixed hypothesis class. Once you have learned, you can throw away the data and keep just the parameters learned, and it's typically specialized. Okay, non-parametric, there are no parameters to learn. It's expressive, it's flexible. You need to keep the data typically though, okay, in order to get this kind of expressiveness, but it's generic and can model anything. Okay, so there are pros and cons of both. Okay, and here we see the pros of nearest neighbor quite strongly. Okay, but the linear model also has a lot of pros. It's this simple model. You've got a tight link from E in to E out, and in practice, we don't know whether we're in the n goes to infinity, n large enough regime, because if you're not in the n large enough regime, nearest neighbor can perform quite badly. And so the linear model comes into its own. Okay. Here's another